All right, so today I'm here to present Oreboot. I'm Ryan O'Leary. Oreboot's a project worked on by quite a few people. Ron is a big contributor. There's some contributors in the crowd today. I see Christian Svensson's here. So who here is familiar with Oreboot? A lot of people. So Oreboot is basically a fork of Oreboot without C code. It's all written in REST. That's the main thing behind it. So in this talk, I'll talk about what Oreboot is, some of the firmware challenges we ran into, some of the challenges we ran into with REST, what targets it supports, so there's a few RISC-V targets it supports, and some design decisions that has gone on in making it. So what is Oreboot? So sorry if I'm missing someone's favorite project here. This is a list of some other open source firmware projects. Like U-boot, Linux boot, Oreboot, Nerf. Big thing behind all these projects, all the existing projects today, is all written basically in C. Most of these use C code somewhere in the project, and that's kind of a across all firmware projects. That's kind of a big common pattern you'd see. And C is kind of an old language, probably like 40 or 50 years old. And what we really wanted to do is use a modern and more safe sort of language. There's also there's other things we're trying to fix in Oreboot. So for example, we want to jump to the kernel as quickly as possible. We want to push as much work into the kernel as possible. We kind of want to use the Linux boot model. We don't want to implement lots of device drivers in the firmware. Linux has great drivers already, very secure drivers, very fast. We want a stricter policy on what is accepted as open source code. We made Oreboot supports a few targets, including RISC-V. It also supports x86 and ARM, but we really want to limit it to platforms which are fully open source. We want to, another big. Okay, so I'll go over what a very simplistic view of what firmware should be doing. So when you power on the system, all it has to do is get the system ready to run your software. We kind of want to cut out from the firmware everything else. Like we don't want a whole network stack, we don't want a whole USB stack. We want it ready immediately to run your software. One of the big goals behind that is a 1 second boot. We want to be able to boot a platform like a BMC or a laptop in 1 second. And really believe if the advances in REST and other things we could achieve this goal, possibly using coroutines or parallelism. REST provides lots of safety in that regard, which isn't seen in many other pieces of firmware. So I'll go over the boot flow of Oreboot. This is very similar to how Oreboot works, but there's a few modifications. So at the beginning we have the boot blob. This is where the first instruction resides. It executes directly out of flash, initializes the CPU and the basic hardware, and it prints a single debug message, welcome to Oreboot. Then it sets up the static RAM, like the cache's RAM, and then it jumps to the ROM stage. The beginning of the ROM stage is still executed directly from flash and has very little memory to work with. Probably about 30 kilobytes on some embedded platforms. And the only purpose of this stage is to initialize the RAM. Once the RAM is initialized, it's ready to jump to an operating system. So the next stage is the payloader stage. So this doesn't deal with network stacks and disk drivers. It jumps directly to the operating system. And the operating system might be one such as Linux boot, which does have the network stack, does have the disk drivers, and that jumps to whatever your software would be. Skip this piece of time. So how many of you are familiar with REST? So, quite a few people. So for Oreboot, we came up with this driver model. So each driver has 4 basic functions: initialization, shutdown, as well as a read and write. So pread is positional read, so read as specific position. So lets you implement stuff like block devices. So here's an example of how you would use the preread function. Just say you had a block device which is 100 bytes. You have your 32-byte buffer. You keep calling the preread function. On this buffer, it reads 32 bytes every time, and eventually it gets to the end. And you pass in the cursor every time you read from it. The reason we do this instead of a read function is because preread is immutable. You pass in the cursor every time, which from a RISC perspective, it's a lot nicer to work with, because in RISC you could have multiple immutable references to the same object. So these are a few examples of the drivers we've implemented in Oreboot. So we have a memory driver which reads directly from memory. We have some serial drivers. We have a SPI driver. We also have what we call virtual drivers. So these kind of work on, they don't work with physical hardware, but they work with, it's a nice abstraction. So for example, just say you have a console in your firmware where you write output to, and you want that output written to multiple devices. For example, if you have multiple UARTs, you could use the console driver, and you give it a list of drivers, and it kind of replicates the output to each one. So this is kind of a nice interface, and RISC makes it safe to implement. If you compare this to C, where they don't really have language support for interfaces, it's a very nice breath of fresh air. And in RISC, you also get printf for free. So printf is part of the core language in RISC. They have a printf implementation which you could write the output to whatever UART or device you want. So for Oreboot, we didn't use CBFS. We didn't use the core boot file system. Instead, we came up with a new system called the DTFS. This is basically a file system implemented using device tree. The main reason behind this is we just have we already had to write a parser for device tree, so we might as well just reuse it for the file system as well in the firmware. You can see an example of one that we put in a 60 megabyte pod. So we have the boot blob at the beginning, and then we have different payloads, etc. And then the other nice thing about a device tree is with Linux, you just pass in the device tree to Linux, and it's exposed under the sys file system, sys/device tree, and you can see all the payloads and items under it. And here's an example for the Sci5 board. This is the DTFS that we use for that. And you can see there's multiple, I think there's 3 payloads here. So this is kind of how we organize the source code for the firmware. We have, it's very similar to Oreboot. We have a directories for the main boards, / the vendor, / the specific main board. We have packages for the CPU, for the SoC, for the drivers, as well as the payloads. Details with the build system. One interesting feature we're using from RISC is it makes it easy to just allocate everything on the stack, which is very useful during early firmware. Everything's allocated on the stack, and you could tell at compile time how much stack you use. There's a tool which tells you. So you could formally prove how much memory your program is going to use and whether it's going to fit in the very small SRAM or car on the system. Another thing we're trying to work out is coroutines. This is for the 1-second boot I mentioned earlier. RISC has language safety features which would greatly help in doing this to make it safe to implement coroutines. This is still a work in progress, and if anyone wants to help out with this, we'd greatly appreciate the help. So the first target we did was ARM, but you're probably not too interested in this. We did ARM QEMU, ARM on hardware, and then we switched to the Hi5 Unleashed board. So it has 5 cores, 5 hearts. It has the heart 0, which has everything but a floating point unit, and then 4 other hearts which are capable of running Linux. At first, we wanted to run it in. We preferred to run Linux in M mode. The idea being, Linux would run in M mode. The user mode would be a new mode. Linux would run without an MMU, so we needed some patches from Christoph Helwig. And We found some challenges with this. Then we switched to using Oreboot with OpenSBI as a payload, and that booted Linux for us, which works a lot better, but we're still trying to run Linux in M mode. The main reason is we wanted Linux to be the only thing running system, like the lowest layer, as well as there's some performance improvements to not having to context switch to M mode. So I could show you the demo of, yeah. So to run it, you just type cargo make. So if you're in the directory for this mainboard, type cargo make run, and it runs in QEMU. And you can see here it booted into Linux, Linux running in M mode, and then it crashed because there's no NITRAMFS. So the next thing that we're working on right now is the next target is OpenTitan Earl Grey. So there's currently no ASIC you can purchase to test this on. So all your work has to be done on in Verilator on a FPGA. It's a more embedded system, so this can't run Linux, so we can't do something like Linux boot. So we'll have to end up implementing more of these drivers inside Oreboot. At this point, it's still a work in progress. We've gotten some simple hello worlds and jumping to some simple payloads, but our main goal is to boot the tar kernel, which is a kernel also written in RISC and targeted for embedded systems. So this is how you can get involved. So we have a Slack, you can join that link. We have the GitHub, you can check it out. We have some documentation on how you can build and run it on various targets. Here's some items you could help us with. We have GitHub issues for these, and if you want to work on it, just ask on Slack and we can get you started. Oli, any questions? Yep.
What are the plans for secure boot in this case? On something like Titan, where you want it to be a hardware root of trust, how does it interface? Are you going to have drivers for like the attestation hardware?
Yes. So we'll need some drivers for for like the AES hardware to implement secure boot. That's one of the projects we're kind of that we need help with. Some verified boot system. Mainly right now we're just trying to get the operating system to boot, the tar kernel. But once we get that part, it shouldn't be too difficult to work out the details of a secure boot system. Oh, repeat the questions. Okay. Any other questions? Yeah.
How about the SBI? Does Oreboot serve SBI calls, or do you use OpenSBI?
So the question is, does Oreboot serve SBI calls, or do we use OpenSBI? So when we use OpenSBI as the payload, OpenSBI serves those calls. We don't have any code in Oreboot to serve OpenSBI calls. When you run Linux in M mode, it doesn't require that. So if you wanted OpenSBI calls, you would just use OpenSBI as a payload.
In library mode, you use it as a library, or you use it as a payload?
Just as a payload. So it's a binary blob.
So you just jump to
Yeah, we just jump to it. All right. Any other questions? Oh, here we go.
Are you open for x86, or do you have a non-x86 policy?
Okay, so that's where things have changed. I have a backup slide for this here. So this is our x86 policy. We put some thought into exactly what the policy should be. The problem is for x86 platforms nowadays, you need some sort of closed source blobs. We're working on like sort of a measure to measure it, like what percent of the firmware is closed source, how much of it is open source. But you could find this policy on the GitHub. I think Ron is sort of starting work on this. Yeah, but the difficulty is you can't make a fully open source x86 system at this point. Okay. Thank you.